Hello, welcome to our paper on deep unsupervised image hashing by maximizing bit entropy. This work is done with Jan van Hermert. I'm the presenter. My name is Yunqiang Li. I will first introduce the background of image hashing. In recent years, hundreds of thousands of images are uploaded to the internet every day, making it extremely difficult to find relevant images according to different users' requests. Usually the images are encoded into continuous features for retrieval. Using continuous features is not efficient for storage and computation. Here, hashing converts original image videos features into compact binary codes by preserving the data structure in the original space. Hashing is very efficient in terms of computation and storage. Here is an overview of our approach. A deep encoder is used to compress the uninput images into k continuous features, and a hash coding layer is used to threshold the k continuous features into k binary codes. We see the continuous to binary transition as a lossy communication channel, yet a hash channel between the continuous feature and the binary variables. Here we design a simple parameter-free behalf layer to maximize the hash channel information capacity. For a hash channel, here we see it as a lossy communication channel. The maximum transmitted information, known as the channel capacity, proposed by Shannon in 1948, is denoted as C here. PU denotes all possible input distributions, and IUB denotes the mutual information between continuous feature U and the binary variable B. To maximize the channel capacity C, we want to first rewrite the mutual information term IUB in terms of entropy. Here IUB is equal to the entropy of B minus the conditional entropy B given U. Thus, maximizing the channel capacity C is equal to maximize the entropy of B and minimize the conditional entropy HB given U. For the first term, the entropy of B, since B is a discrete binary variable, it only has two possible values, +1 and -1. Just like flipping a coin, the entropy of B is maximized when it is half-half distributed. So the probability of +1 is equal to probability of -1 is equal to 0.5. For the second term, the conditional entropy HB given U give a certain continuous value U. It is computed as the following equation, where the transmission probability PU pulse and PU neg are defined as how probable a +1 and -1 binary output value are. Since they both are probability, so their sum is equal to 1 and both are larger than 0. So the conditional entropy HB given U here is between 0 and 1. The minimum value is 0. This minimum is obtained when either Pu pulse or Pu neg is equal to 1. In this case, it means that there's no stochasticity for a certain continuous value U, and its binary value is deterministically transmitted. As a summary, we have two conditions. The first one is the binary value should be half-half distributed. The second one is the hash channel should be a deterministic transmission channels. In the following, we will maximize the entropy of binary variables by encouraging the continuous feature to align with the prior half-half distributed distribution, and to minimize the conditional entropy, we will first start with a non-deterministic transmission probability during training. But since we train to align the continuous distribution Pu with the half-half distribution, this allows us at test time to simply use the sine function as a deterministic function for quantization. To align the continuous feature distribution with the ideal prior half-half distribution, we here use the optimal transport. What is optimal transport? Simply speaking, optimal transport aims to find a minimum cost by moving a probability distribution Pu to another probability distribution Pb. When the Pu and Pb are only accessible through discrete samples, we use the corresponding empirical distribution to compute the optimal transport cost. Here, if we use M as a mini-batch sample, and we can denote the probability Pu and Pb by the discrete sample. The goal is to minimize the optimal transport cost to find the optimal transport coupling pi0. Here, we use the 1 Wasserstein distance because it is easy to optimize. As the equation pi0 is the optimal transport coupling, pi_ij is all possible coupling. Ui is the position, the continuous bj is the position of the binary variable. Here bj can only be -1 and +1. Minimizing the previous 1 Wasserstein distance, here in the Hessian case, since the b is prior half-half distributed distribution, we can get a closed form solution. For a single hash bit with m samples, the continuous feature vector u, we will first sort u over all possible images, and then assign the top half elements of sorted u to +1 and the remaining elements to -1. That is the following equation. Here we implement the quantizer as a new simple hash coding layer. We call it a B-half layer. In the figure, M is the mini-batch samples, K is the feature dimension, also known as the hash bit number. For each hash bit, we use the optimal coupling to binarize the continuous feature in U to binary codes in B. The proposed B-half layer can be easily embedded into current deep architectures. It can automatically generate higher quality binary codes. And the B-half layer is simple and is parameter free. For the optimization, since the discrete binary codes B have no continuous derivatives, and it cannot be directly optimized by graded descent. Here we use the straight-through estimator proposed by Bingo in 2013 to obtain the gradients. Here we summarize the forward and backward paths. The experiments, we conduct experiments on 5 image datasets and 2 video datasets and 4 architectures. For the experiments on autoencoder, we train an autoencoder with a deep encoder and decoder. Encoder and decoder. For our B-half layer, we will append after the encoder to generate the binary code. Here is the visualization for the continuous feature distribution with 3 hash bits. Here we compare 3 different methods: sine layer method and sine plus a regularization. Here we use the B.1 as the regularization term, balanced with the BCE reconstruction loss through a hyperparameter alpha. From the visualization, we can see that our B-half layer can automatically encourage the continuous features into half-half distributed distribution. This figure shows the retrieval performance, where the left 2 subfigures show the effect of hyperparameters. In our paper, we use gamma and alpha as a hyperparameter. From the result, we can see the proposed B-half layer outperforms the sine layer and the sine plus regularization layer. Because for the sine plus regularization, it needs to tune the hyperparameter alpha. For our behalf layer, our behalf layer is parameter free. For other 4 image datasets, we use a pre-trained VGG16 on ImageNet as our backbone, and our behalf layer is appended to generate the binary codes. The table shows the MAP results for different state of arts on 3 datasets. Our methods with 16 bits outperforms others that use 64 bits. So it is efficient in computation and storage. This figure shows the top-end precision and precision recall curves on MS-COCO dataset for different methods. The proposed behalf layer outperforms other methods. We also conduct experiments on the video dataset to do the video retrieval. Here we present the MAP 100 results for 2 video datasets using 2 pre-trained 3D ResNets on kinetics. The same, our behalf layer is appended to generate the binary code. Our proposed methods outperforms the same layer-based greedy hashing method in a large margin. Thank you. Meantime, our code is available online. Thank you.